Hopefully by now you've finished your graph and it looks something kind of like the one you see on the screen. It's obviously not easy to plot all of these points super accurately, so even if you got something that generally resembles this shape, you're fine. Now, if you remember this shape from before, this is actually the exact same shape we saw on page 6, way back at the beginning of the chapter. But again, if you didn't finish your graph back then, or if you did finish your graph but it didn't really look exactly the same, this should give you a chance to kind of get yourself mentally reset a bit. Now, I've actually gone ahead and done something by default that answers question letter G. So let me quickly explain. It in letter G asks, should this graph be continuous or discrete? And that's not vocabulary that we've learned in quite some time. That was actually first semester vocabulary. So I'll just remind you that the word continuous actually just means connected, and the word discrete, by contrast, means disconnected. So if you're looking at this and asking yourself, ooh, should it be connected or not? You might kind of have inferred from the fact that I connected mine that it probably should be continuous. The reason is actually because technically, in between these tick marks, there are lots of other angles on the circle. Remember, the tick marks are just values on the circle? Like, for example, pi over 4 and pi over 3 and pi over 2. Those are just spots on the circle, stops where the Ferris wheel could have theoretically kind of stopped its journey. But in between any of these dots, there could very well be a stop. It wasn't a special right triangle necessarily, but between 45 and 60, for example, we could say, well, like 55 is in there somewhere. And then 58 is in here somewhere, and 59 is in here somewhere. We didn't measure all of those individual spots, but we know that there are spots for all of the numbers in between every single stop that we did measure. So because there's really all sorts of extra numbers in the in-between dots sections, I do want to make sure that my graph is continuous or connected because it represents all of those little in-betweens, all of those points that we didn't individually measure. But if you really think about it, and I'll use this zoom to the best of my ability here, when you really think about it on the most microscopic levels that you can possibly think about, if this first tick mark was the seat at 30 degrees, all of these individual little dots, so almost like all of the individual tiny bits of graphite that I put down on my paper when I connected the dots, represent the heights at seat with 1 degree, 2 degrees, 3 degrees, 4 degrees, 5 degrees, 6 degrees, 7 degrees, 8 degrees, all the way to this first stop at 30 degrees. So that's kind of what's happening when we connect the dots. It's really just meant to represent all of those other points that we didn't individually measure, because Lord knows that would have taken a really long time, but are theoretically there. Now, in letter H, the hypothesis that you can start to make naturally is, what do you think will happen to this graph as we keep going? So if naturally you kind of saw the pattern go up and then back, and you kind of noticed you almost ended up back at the beginning again, think about what would happen if the graph went further, if this 2 pi wasn't the end of the graph and it kept going off to the edge of the screen. Naturally, you can probably kind of picture the pattern simply repeating itself. And that is actually what's going to happen. As the graph goes further to the right, it's actually just going to repeat the exact same pattern. So, when it relates to the Ferris wheel, you can actually think of that in a logical way. If the first cycle of the graph represents all of the heights all the way around till I get to 360, then past that, it's all just going to repeat itself. Once I take a full ride around the circle, I'm just going to start over again. And the whole graph, the whole cycle, is going to repeat itself. So again, I'm kind of saying the answers to some of these questions without writing them, but hopefully that makes enough sense that you can explain it in your own words. I suggest, if you can, pause the video, make sense of this idea, and write a response to letter H in your own words before moving on to the next page. If you're ready to move on to the next page, we'll kind of continue the same sort of idea in question number 2. Now, instead of doing one cycle of the circle, it's going to extend what we call the domain. Now that's a fancy way of saying it's going to extend the endpoints of the graph. So if you look carefully at the graph in letter B, you can see that instead of stopping at 2 pi, it stops at 4 pi. So in letter A, it says, how many cycles of the sine function does this represent? Let's use a little bit of logic for this. One full cycle of the graph, one full ride around the Ferris wheel, is 2 pi. That's a full circle, otherwise known as 360 degrees. So if one full circle is 2 pi, and every circle after that is another 2 pi, and another 2 pi, and another 2 pi, then just think, 4 pi is like having two 2 pi's, so this must represent 2 cycles of the sine function, or 2 rides around the Ferris wheel. The follow-up question asks, do we really need to make another table to determine all these necessary values for a graph? It doesn't seem like it, because if I take another ride around the circle, all of the heights are still going to be the same. I'm going to have 1/2 and root 2 over 2 and root 3 over 2 and 1 and root 3 over 2 and root 2 over 2 and 1/2 and 1. I'm not going to need to redo all of those numbers. I already have those numbers in the big table in letter E. So there's not much of a point in redoing the whole table. Let's just recycle some of our values. And that means when we plot the points in letter B, it may be helpful, if you can, to sort of fold over your paper in a creative way. You can see that I'll try to do this as best I can, even though it's not going to work out too well with this camera angle, to see the values from letter E while I'm making the graph on the next page. So just to kind of demonstrate this back and forth, here's what I'm going to do. I'm just going to mark for the tick marks they specify only. So you notice there's some of the in-betweens are missing. That's good news. That means I have less dots to plot. But I'm just going to recycle the dots from the previous graph. For example, if I want to make a dot at 0, I'll check back to my table. 0, 0 was that point. So I'll plot 0, 0. Then I'll look at the next dot, pi over 2, and I'll look back. Pi over 2 was 1, so pi over 2, y-coordinate 1, and I'll plot that dot. Then I'll do the next one, pi. I'll look at my table. Pi was 0, so pi 0 is here. And then I have to make a quick inference. Remember, 3 pi over 2 was from that bottom half of the circle that we said we didn't need to make a whole nother table for. But if you remember, 3 pi over 2 from your previous graph, 3 pi over 2 had a y-coordinate at -1 down there at the bottom. So, -1 it shall be. And then going back to my graph one more time, I didn't have 2 pi in my table, but I had it on my graph. 2 pi was 0, so I'm going to borrow that point again. Now you can definitely tell that the scale of this graph is going to look a little bit different. It's going to look a little bit more squished in, so to speak. But if I connect the dots, we'll definitely get that same kind of wave pattern that I had the first time. And we can make a hypothesis. If after 2 pi, the cycle just repeats itself, the dots are going to repeat themselves. So if 2 pi is kind of like the beginning of our next new cycle, then watch as I kind of point to what's happening. That means the next ride across the circle is going to take me to a top point up here at 1. And then if I keep riding along the circle, follow my finger on the left as you watch my pencil on the right, the next dot would be this one here, back at 0. And then if I keep following the pattern, I know that I'll get down to this next dot here, which is at -1. And then, of course, if I keep it going all the way back up, it looks like I end back at 0, which does actually make sense, because if I took another ride around the Ferris wheel, and again, I'll just go back to my reference here, if I took one full ride around the circle and then a second full ride around the circle, there I would end up at 0 again. So that definitely makes sense as a y-coordinate. If I connect these dots, you can definitely start to see a pattern emerging. You can definitely kind of see this wave pattern. Now in letter C, it says on your graph, continue using the pattern backwards. So let's see how this would look if I keep the pattern going in reverse. If I think about going backwards, I'm going down and then up and then down and then up and then down. So if I figure the pattern goes backwards, then if I keep reversing using an existing part of the circle, looks like this y-coordinate would be at -1. And if I reverse my way again, it looks like I'd be here at 0. So if I connect those dots, I can definitely tell visually that seems like it works, because now the graph looks like it's one smooth, flowing, continuous curve that definitely has a pattern to it in and of itself. Now in the actual question it says, describe how negative values of x are possible on this graph. We've actually seen negative values on the unit circle. If we go backwards, the negative values are just kind of the coterminal angles that we've already seen. So you don't really have to describe too much in detail here. Backwards just basically means you're going to go around the circle in the opposite direction. Normally when we go forwards, we start from 0 and go up. Negative values, by definition, just involve going backwards, starting at 0 and going in reverse down to the 4th quadrant and back around in the opposite way. Again, if you want to pause this video and take some time to make some sense of that idea before you write down an answer, I suggest you do so. Once you finish that idea, take a moment to really kind of step back and make sure that you understand everything that we did in question number 2. In question number 2, we really did start to see the emergence of this shape. And this shape is officially going to be the graph of all functions sine, which means that this is the official equation that goes with this graph. Sine x is going to be, from this point forward, an equation we're going to talk about as a graphable equation, not just the heights on the unit circle, not just part of SOHCAHTOA, but an actual graph, like a parabola or any of the other curves we studied this year. So before you move on to the next video, you might want to write the words sine somewhere near, or the word sine somewhere near one of your graphs, and make sure that you start to make that connection. We already know, for example, that when we see equations that have squares, we think of parabolas. When we think of equations that have square roots, we think of the little half parabola. So now when you think of an equation that has sine, picture this wavy graph, and that association will start to get a little bit more obvious once we do more of them. In the next video, we'll start question number 3. So take some time to just make sure that you digest all this information before starting the next video.